Hello everyone, welcome to the LLM show, and I'm your host Shamin City. In this episode, I actually want to talk about this amazing paper about how to utilize language models to build sequential recommendation systems. The paper name is Text is All You Need, Learning Language Representations for Sequential Recommendation. So we actually discussed about why recommendation systems are so important in the field of machine learning, and also how large language models can kind of help to improve these like traditional recommendation systems. So this paper is more of like how we can kind of create a recommendation system that uses textual features as well as transform architectures. And yeah, let's go through the paper. And the paper is from Amazon recommendation team, and I really enjoy reading this. The paper is crystal clear and all. So yeah, without talking much, let's go to the paper. So abstract says like sequential recommendation aims to model dynamic user behavior from historical interactions. So just to like clarify that, so what is a sequential recommendation system? The idea is pretty simple. I think you can see my screen. So imagine we have a user called Jimmy. So we also have that users in previous interactions, like whatever he has done. So given that kind of a sequence, our model should be able to predict what Jimmy might do next, right? So it's the same for Tina as well. So this is basically a basically the core concept behind these sequential recommendation systems, right? So then they also mention in the abstract like we already have sequential recommendation systems, but these sequential recommendation systems usually use things like item IDs and user IDs as features. So the idea is like, in order to feed this information to a model, we might need an ID or an ID embedding for this item. So then the main problem with that is the call start problem, because once there's a new item, what happens is you have to retrain the entire system, right? So that's a big no-no in the field of recommendation systems. And also solving the call start is like the biggest thing right now, right? If we can solve this call start problem, that we might be able to kind of get better results and all. So just to summarize, call start is basically like your system loses its ability to kind of recommend items to new users, or recommend new items to existing users, because you don't have those interaction data. But like this paper says, like if we represent everything in text, what happens is we actually can build a recommendation system without that call start problem, right? So the idea is actually simple, right? Like, because if we can represent all these user interactions in the text space, like maybe the name of this action, or like any sort of a textual feature. So thing is like, then like everything is in the language space, and if there's something new we need to infuse, we can easily do it, right? Because everything is in the text. So they say, to this end we present a novel framework named RecFormer, which effectively learns language representations for sequential recommendations. So yeah, they mainly explain about this. For recommendation, RecFormer is trained to understand sentence sequence and retrieve the next sentence. So the idea is like they think like we can represent the user as a sentence as well as the next item as a sentence as well, right? So basically it's all about matching these two representations. To encode item sequences, we design a bidirectional transformer similar to the model long former, but with different embedding layers of sequential recommendation. So they say like their system architecture is a transform architecture. So what is this long former? So we can quickly Google it. So basically long former is a transform architecture that can handle longer sequences. So long form is a modified transform architecture. Traditional transform based models are unable to process longer sequence due to their self-attention operation, which scales like this is like n squared with the sequence length. So long former basically we had, so this is like they have modified the attention and all, so you can read about long former and you can easily load this model from Hugging Face Transformer Model Hub as well, right? Yeah, let's go through the code, let's go through the paper. And then in the introduction they again mention like traditional sequential recommendation systems, they use this item ID and their corresponding embeddings to build the sequential representation. So then the problem is there will be we can't solve this call start problem, right? Because once we have a new item, we don't have that embedding and we actually need to train everything from scratch. So then they say like their basic idea of their model. The basic idea is to employ pre-trained language models such as BERT to obtain text representations and then learn the transformation from text representation to the item representation. So in other words, like if we can represent these interactions or sequences with text, also items with text, it's easy when there's a new sequence or when there's a new item, we can easily kind of get representations for them if we have a pre-trained language model. So yeah, idea is kind of pretty simple in that way. So yeah, we'll come back to the figure. Actually we can say like so yeah, the figure 1, input data comparison between item IID sequences for traditional sequential recommendations and key value attribute pair for sequences used in RecFormer. So what they say is, so this is the item sequence, this is like what you would collect in your company, and laptop, mouse and iPhone, then what next, right? So in previous ones, what we used to do is we have this ID and then we have some sort of an embedding table. For each ID we have an embedding, so which is a trainable embedding in the beginning. So we kind of represent this each ID with an embedding. So yeah, you should remember embedding table storage NN. So in RecSys, yeah, like this is like pretty much an embedding table, right? So what they say is, in our work what we have is kind of this like we have like transformed each item into a key value pairs. Like don't think much about this key value thing, you will understand, but the idea is how they have formed this data, right? Because you need to somehow come up with a structure to this data. And yeah, that is like you have the title of the item, and you have the brand of the item, you have the color. So what they have, so their main thing here is like we will go there in the paper, but the idea is like they wanted to come up with this kind of common key value pairs for every item. So usually their assumption was like for every item we can find these keys, title, brand or color, so it's same, right? So then kind of use these text representations to represent the sequence. So that is pretty much that. Yeah, then in the figure 2, model input construction, so which is pretty simple. You have this special token title, then you put the title, and then you put this special name brand. So this could be a special token, but they have just used the title just like the text, and then brand, and then you put what is the brand, this is the key, this is the value, and then this is the color, the key and the value. So yeah, this is like the nice sequence. And what happens is here you will have like several sequences, like several representations. So this is the representation of item 315, and for 235 also there will be kind of a same representation. and you will concatenate everything before you feed into the transformer to represent your user. So yeah, here the user is like this, right? This is where, and you need to predict what this user might purchase next. Yeah. So then they say like the problem, like what they haven't just used a pre-trained language model. What they have done is they have done some pre-training as well. So they have their reasons like why they actually train their own transformer, or like pre-train. They are not just use a checkpoint. So the idea is, however, like BERT-like frameworks for learning transferable language to items have several limitations. So first one is, pre-trained language models are usually trained on general language corpus, serving natural language tasks that have a different language domain from item text. Example, concatenation of item attributes. Hence, text representations from pre-trained language models for items are usually suboptimal. So the idea is simple. So if you take a BERT or like the original long former, they have trained on general data. So that data is kind of, that textual data is different from how we represent these item representations and everything. But again, like I don't know, like if we use a thing like large language model or a humongous sentence embedding model, sometimes this might be okay, because that model should be good enough to kind of understand even the text from like text from the e-commerce domain. But yeah, this is just my opinion. I haven't seen any fact regarding this, but for now what they say is makes sense, right? So maybe like that it would be better. That's the idea. It would still work, but it would be better if we pre-train our own transformer with this textual data. And then the nice part, text representations from pre-trained language models are not able to learn the importance of different item attributes and only provide sentence level textual feature, but cannot learn fine-grained user preference for recommendations. So here the idea is like what they're saying is, if we encode our representation for an item like this, still we can't guarantee that the model would learn this kind of stuff. This is the title and this is the brand, like more like the key value things, right? And this is the color key, and this is the gold color, like that. So what they're saying is transforms are good at like getting the sentence embedding, like sentence level, which is like the context, like what they're saying is so they wanted to come up with some sort of solution for this. So yeah, we'll see. Like, so first one, second one, third one, due to the independent training of pre-trained language models, like what they're saying, independent training means usually any transform model you will see in Hugging Face transformer. So like anywhere what you will see is like they have this there are training mechanisms. Like one such mechanism is MLM, mass language modeling, next word prediction. Even we have sentence transformers that has trained on in-batch negative contrastive loss, those kind of stuff, right? So what they're saying is still they are very different from our own task. So can we do some pre-training by kind of combining some sort of a pre-training task with in this recommendation domain, right? So that's that. So what they're saying is they have kind of picked these three limitations, and because of that, not only they apply this text, like they applied transformer networks to create a text-based sequential recommendation system, but also they came up with a new transformer architecture, right? That's their main idea. Then so they say like why here, what the idea is like, we can represent this stuff in different ways, but the most universal form is the text. So the input is entirely text, nothing else. And yeah, so the basic idea of this paper is to use the generalizability or generality of language models through joint training of language understanding and sequential recommendation. So we'll go like we'll see like what this actually means. Yeah, like then they say how it would help. And overall our approach takes a text sequence of historical items as inputs and predicts the next item based on the language understanding. So again, so I explained about this, but the idea is like you can represent some users by their historical interactions, but now each interaction is a text snippet, right? So this is like that text thing, each interaction. So you have now a bunch of text in a sequence manner, like so, like keeping like maybe like like the most recent one at the last, and then once you have this sequence, your model needs to like kind of predict or find what would be the next item. That item also is represented in text, right? Then they say that's what is in figure 1. We have already discussed about figure 1. Figure 1 is this, and figure 2 is how we transform those key values into a sequence. All right, then they again mention about their key findings here, but I'm not going to go through. We already have discussed. So now let's come to the problem formulation. So they have a bunch of keywords like key, I don't know, symbols. So the idea is like this is like pretty normal in sequential recommendation systems. So we represent an item as item set as like block I, and a user interaction sequence. Like if you have, so let's say this is about Jimmy. So this is like you represent this user as like a sequence of items, like in a timely manner, I1, I2 into IN in temporal order, where n is the length of S. So we can define like are we taking like what is the length of this sequence. We can define like are we taking last 10 days worth of data, last 1 hour worth of data, or last 1 month. So it's up to us. And then each item I has a corresponding attribute dictionary, key value pairs. That's like item name and the name, item brand and the brand, like color, and like we talk about that dictionary, like key value pairs. And then what they say is like in order to represent a single sequence or like an I, what we do is we transform each each these key value pairs into like we concatenate it. Yeah, so that's like the sentence. That's so basically we represent an item as a sentence. So that sentence comes by kind of combining these key and value pairs, right? So yeah, that's pretty much it. Here the terms you need to understand. Then the rec former. So they again say rec former is like similar as long former. Why long former? Because it can handle longer sequences of length, because they have this modified attention. So this is also an important point, because when it comes to recommendations, in some domains we might need like longer sequences. So better to go with a model like long former, because you can then represent your users with the longer sequences. So that's pretty much it. So model inputs as introduced in section 2.1. For each item I and corresponding attribute dictionary di, we flatten the dictionary into an item sentence. So that is pretty much what we have just discussed regarding this figure, right? So we flatten it, so that's a single item. And then to encode a user interaction sequence, I1, I2, IN. We first reverse items in sequence because intuitively recent items are important for the next item prediction, and reverse sequence can make sure recent items are included in the input data. So what they're saying is they needed to make sure like somehow most recent items are always included in the input data, because sometimes, you know, if the idea is like if your sequence length is bigger than the max token length, so there will be a truncation, so you don't want to lose any recent data. But yeah, you can do this by also like taking the last n elements or something. But yeah, then what they're saying is they also appended some sort of a special token, which this special token is the class token. So they just use a class token in the beginning, where X is a sequence of words containing all items and corresponding attributes the user interacted in the history of like interactions. So this is pretty much the entire user. So yeah, like that's pretty much it about the how we transform model inputs. This is like the input layer, and then the embedding layer. So this is where things get a bit tricky. Not tricky, like this is one of their main contributions. So the idea is if you are using a pre-trained long former, the thing is like you have to input this as a sentence, like all these different items in the sequence, you know. So then what you might need to do is like to represent like all these items after an item. You can also add some kind of a special token, and you know, you can just create the sequence, create the input sequence. But in this paper they have done a different thing. So let's see what is it. So they have kind of modified the embedding layer of the long former. So let's see how they have done this. So the target of rec former is to understand the model input X from both language understanding and sequential patterns in the recommendation. So the idea is they need to infuse language plus this sequential interaction, like feedback or implicit things to the representation. The key idea in our work is to combine the embedding layers from language models and self-attentive sequential recommenders. So yeah, so let's see like what are the main differences. So now they have a token embedding layer, which is like pretty much I would say pretty much a normal thing. You need to have a token embedding layer like in the transformer. Like if we quickly type transformer token embedding layer, oh my goodness. Yeah, like so this is something like that. You have the input for each token, you know, like this could be like byte pair encoded tokens like after the tokenizer, and for each token there's this embedding. So that's, you need to have that. So token embedding represent the corresponding tokens. We denote the word token embeddings by A. So this is like the dimension of this entire token matrix. So PW is number of words, right, and in our vocabulary, and D is the embedding dimension. So it's pretty much like you can use a normal tokenizer, and well, there's nothing fancy about this. Also they mention, unlike, this is mainly for this recommendation community, unlike good old day sequential recommendations, we did not create an embedding table for each item separately, because the thing is, if you do it and if you train with that, when there's a new item, you can't you can't compose it to the sequence, right? Because you don't have the embedding of that. So basically you need to train another model for that. So whole idea of this paper is to not to do it. So yeah. Then token position embeddings. So this is a new so represent the position of tokens in a sequence. A word appearing at the ith position in the sequence XX is represented as PI, similar to language model tokens. Token position embedding is designed to help. So yeah, again, this is also same as a normal transformer. So in a normal transformer we have to have positional encoding, so they also need to have positional encodings for each token. So yeah, like there are different positional encodings, sinusoidal, trainable, or right now rotary embeddings are getting pretty popular because we kind of can there are like new work. If you use things like raw form embeddings, rotary embeddings, you kind of can upscale them even after the pre-training. So yeah, so and the last then we have another two. Then this is new, token type embeddings represent where a token comes from. Especially the token type embeddings totally contain three vectors: key, value, class, key, value. So it's kind of so it's like, remember, like we so here remember, like we talk about like this, like key value. So this is title, and for this is like MacBook, the title of that. So you need to say the model like, okay, here this thing is actually, this part is actually this I don't know what is this color, like it's like pinkish, like whatever, it's orange, pink, or whatever. These two chunks come from this this key called the title, right? What is this chunk of the this chunk of this item representation? So different types of tokens, they say different types of tokens usually have different importance for the next item prediction. So the next one is item position embedding, represent the position of items in a sequence. So it can actually say like to the model, okay, this part of information is relevant to this item, and the next part of the information is relevant to the next item. So yeah, that's pretty much these embedding layers. So this is like the main contribution in terms of the, I would say, architecture. And first two embeddings are same, token embeddings and token position. Then token type embeddings to identify which type of like these keys and values. And then also like what the item position, like this chunk of information is relevant to this item. Now let's go to the figure 3. Figure 3 explains the entire idea of this token embedding layer. So okay, so let's say we have a bunch of items. So you need to start your like sequence with a special token class we just discussed, and then you have key values for an item and then key values for another item, right? So first one is item position embedding. So from here to here, all these tokens are relevant to our first item, right? Then what we do is we input a special item positional embedding saying like this is D1, this is also relevant to D1, this is also relevant to D1, like that. Then when it comes to the second item, all the tokens are relevant to D2 embedding, so like that. So then what happens here is the transformer knows, okay, this part is belong to one item and this part is belong to another item. So that's what happens. Then the token type embedding, so this is the type, this is C class, this is C key, and then this could be another bunch of tokens. For each token we kind of use C value embedding, and yeah, same, we do this for same thing. And these item type embedding tokens are shared between different items. So model knows, okay, now after this token we are talking about the title of that item, like that, right? And then token position embeddings, we have discussed, there's nothing much. And then token embeddings, right, same as the normal transformer. Then yeah, we send it through the transformer and we get the output. So this is pretty much the architecture and the embedding layer, but yeah, you can always further read about this, but for now I would say this is enough to kind of understand the core idea. So yeah, they kind of use all these embeddings together before the layer norm, and they use the class token to actually represent the sequence. They will explain it later. And yeah, that's pretty much it. So yeah, that's the class token thing. Yeah, so now this part is really important to understand, the prediction part, right? Prediction, we predict the next item based on the cosine similarity between users interaction sequence S and the item I, right? So what is this cosine similarity? If you go to like something like this is what happens. So now you here your network is like actually the rec former. Because since you are using text, you can always use the same model to represent user sequence as well as the item sequence. So item sequence is actually similar to a user sequence, only with a single item, right? That's pretty much it. So this is the user sequence, this is the item sequence, and this all the parameters are being shared. You have two embeddings, and then you can get the similarity loss. So what they are doing is they are using cosine similarity between the user sequence representation and the next item, right? So it's not like you try to predict like as predict the next item as a token, because if you try to do it, what happens is again you need to have fixed set of embeddings for each or like fixed set of tokens for each item, right? So it's not like predicting the next word like a language modeling, but what you do is with this thing you kind of you kind of can create a representation for your user sequence and the representation for your item, and then you can kind of get the cosine similarity. So the correct next item should have a high score, and the other items should have a low score. So let's go to the learning framework. So in the learning framework, you have a pre-training phase and a fine-tuning phase. First we will check the pre-training phase. So what they're saying is they could have trained this only with contrastive learning. Contrastive learning is like matching the similar embeddings with similar things. So basically this is like the pre-training. So you have the user interaction sequence, and then you have the item interaction, you have the item list, then you kind of encode each items and then kind of compute the contrastive loss, right? So yeah, what is this in batch negatives? It's not a big thing. It's in batch negative. This is a good example to identify in batch negatives. So this is from the clip paper. Just here you can always like substitute this text encoder and image encoder to the rec former, and this is like the, let's say, user representations. These are like the item representations. So we take a batch during the training, like let's say 128, and we know like for each example in the batch there's a positive example. We know this is like the correct next item, and all other things we take them as negatives, right? So you can see for this item and for this item representation and this user representation, the correct representation, like once you like kind of like get the cosine score, this score should be the highest in a perfect scenario. All these other scores should be the should have low values, because they are not these matching items, right? So that's pretty much the in batch negative contrastive learning. Yeah, please read about in batch negative contrastive learning if you want to know more, but there are heaps of information, heaps of tutorials on that, also very really good papers. So but what they're saying is, rather we could have done it, but it's not like that. What we wanted is like to kind of somehow inject the semantic informations as well, you know, like, because we just didn't want to override it only with contrastive learning. So what they have done is they have also infused mass language modeling. That means that's why here you have this mass token. So it's like a joint loss function. You train this with contrastive loss, you pre-train this with contrastive loss, as well as you kind of have this predicting the mass language token loss as well, you know, MLM loss. So they have combined both of those loss functions. So they say adding MLM loss as an auxiliary task will prevent language models from forgetting the word semantics when models are jointly trained with other specific tasks. Yeah, so that's the main thing. You need to make sure they, like, our transformer still knows about semantic information. For that we have added the mass language modeling. So how they have done mass language modeling thing, so like what they're saying is they just followed other stuff like BERT. So what they're saying is the training data generator chooses 15% of the tokens position at random for prediction. The token is selected, we replace the token with mask with probability of 80%. That means so the idea is like this. So you have now you need to infuse MLM loss as well. So if you have a sequence of these item representations, and obviously they have different tokens, and then they kind of pick 15% of the tokens randomly every time. Then once let's say you pick the second token, right? Once you pick the second token, 80% of the time you will replace it with the mask. That means then once you have this mask, the model knows, oh, I need to do the mass language modeling, then I will back propagate the loss regarding this, right? And then 10% of the time what they have done is they have not replaced that with the mass token, but with a random token. I think that's because like you still need to do the contrastive learning. For the contrastive learning you need to have a sequence, right? It would be right. That's why I think they have, because otherwise they don't need to do this. And then 10% of the time although they don't change the mass token at all. So I think then they also don't compute the loss like that. So but that's the idea, like how they have infused mass language modeling. Then they say another pre-trained task for RecFormer is the item contrastive task, which is widely used in next item prediction for recommendations. So that's pretty much what we discussed. We use the ground truth next item as a positive instance for instances following previous framework. Yes, so the correct one is like we adapt in batch next item as negative instances instead of negative sampling. Negative sampling is you can kind of, for every example, every user sequence, there could be a positive example and maybe 10 different like negative examples. And also there's a thing called fully softmax. That means for every time when you encode the positive example, when you encode the user representation, you know what is like the positive item. And then for negative items you can take all these items in your corpus, right? Then you can do a fully softmax, like literally like finding the correct cosine score. but they haven't done it. Why we, so it's, I don't think this is more like theoretical thing, because if you do this, both of these things are quite slow. In batch negative method is quite fast. That's why we are using in models like clip, and even these recent sentence transformers like E5, even dense passage retrieval, those kind of stuff. So yeah, in batch negatives are really good. They say in batch negative instances are using ground truth items of each instance sequence in the same batch as negative items. So for every user sequence there's one positive example, and negative examples comes from other positive examples, right? So yeah, that's pretty much the in batch negative contrastive loss. Yeah, so then they say like it's okay, using in batch negatives did not hurt us. Also, like we don't need fully softmax or like negative sample in during the pre-training, like that. So then the fine-tuning thing. So now you have this transformer which has already trained. For the fine-tuning also, they have two-stage fine-tuning. This is also a bit tricky thing. It took me quite a few iterations to understand, but the idea is pretty simple. I really like the idea. So what they're saying is, now you have a trained model, but then when you want to fine-tune it for your own data set, sometimes the thing is in batch negative contrastive learning could go wrong. Right now for this task you don't need mass language modeling. You have the checkpoint. All you need to do is like you have the user sequence, you get the representation, and then you have the item sequence. You have the item and you get the representation and apply contrastive learning, right? So this is basically this is pre-training, but this is what you need to do in fine-tuning right now. But what they're saying is they don't want to use this in batch negative thing, because why? Sometimes if your data set is small, there could be some kind of false negatives, because sometimes if your data set is small, sometimes what happens is you can get like a correct example, like matching item as a negative item as well. So that's not good. So that makes sense. So when you read this contrastive learning paper, like papers like clip from OpenAI, they mention about this thing. So when the data set is big, it's all right, like although there might be some false negatives and all, so it's not much of a big deal. But what the authors of this paper says is, of course, when it comes to our specific data set where you need to fine tune, in batch negatives can hurt. But again, that means if you have a good enough big data set, you can still use in batch negatives. So I hope you get the idea, like how when the data set is small, how we might get false negative, we might get these false negative scores, right? Because that means like if the data is small, so now in our batch we think for this user the correct item is item 1, but actually what happens is item 2 also kind of correct for this user, but when you are taking the softmax, we only take like this score as the correct one. That's the problem. That's what happens, right? Now so that's why they are saying like, okay, we have this amazing two-stage thing which is kind of efficient as well. I think this two-stage thing, the main purpose is like they need to make sure the accuracy will be a good one, of course, and also like the efficiency. So what they do is we propose two-stage fine-tuning as shown in algorithm 1. The key idea is to maintain an item feature matrix I. So now when you're fine-tuning for your own dataset, yes, you can still keep an item feature matrix, right? So different from the item embedding table, I is not learnable, and all item features are encoded from RecFormer. So someone could ask, oh, isn't this the same? Like we have now trained a transformer, and for the fine tuning phase, we have some bunch of item embeddings. But what they're saying is this is not an item embedding table where in good old days sequential recommendations you had to fine tune, but this is more like kind of like an item feature thing. Each feature get encoded with this pre-trained RecFormer, right? So that's the item feature table as shown in algorithm 1. Our proposed fine-tuning method has 2 stages. So yeah, so we kind of we can go through this. So this is the dataset trained, this is the validation dataset, this is the item, that's what do you call item feature table, and this is like the model means model checkpoint, then the number of epochs, and yeah. So you initialize with pre-trained parameters. Now you load these pre-trained parameters of the model, and p metrics are initialized with zeros, of course. And then what you do is in stage 1, I is updated per epoch. So what they're saying is like, so you, let's say in your data set you have like 10,000 or 1 million unique items. So what you do is in the start of the epoch, you encode all these items with the model, right? Model. So now you have a bunch of item vectors, right? Where in stage 2 we freeze I and update only the parameters of the modeler. So yeah, now it's easy to understand. So what they say is like, now you first, for per epoch, you kind of update your item embeddings, and then what they say is they take the fully softmax during the fine tuning. Now they don't use the in batch negative, so fully in batch negative, but what they use is like the fully softmax. Fully softmax is you take your item embedding, right? You take your you take your user sequence embedding, and then you match it with all the item embeddings from that item feature table, and you get the cosine scores, and you can apply this softmax function cross entropy, because because here okay, for this user representation I know this is the correct one, all other things are negative ones. So that's pretty much the fully softmax instead of in batch negatives. So the main difference is during the first stage we only encode this item embedding feature table like per epoch. So what happens is, why we are doing this per epoch, because what they're saying is it can create some sort of instability, and also, I mean, practically it's more efficient, right? Because they are also using this full softmax, which is also could be like could be expensive if you want to update this feature table. And once you are finished with the first stage, in the second stage what you are doing is, then you don't even touch the item feature table. You just freeze it with your model parameters after the stage 1. Then you just optimize the model in the stage 2. So what they say is since I keeps updating in stage 1, the supervision for fine tuning is also changing. In this case, the model is hard to be optimized to have best performance, because in the I, even in every epoch, like model also even in the first stage, since we change I in every epoch, it can make the life harder for the model parameters to get optimized. But what they do is, in the stage 2, we freeze I and continue training the model until achieving the best performances, right? So that's pretty much it, like the 2-stage fine-tuning, and I hope you get it. The only difference is they have 2 stages and they use fully softmax loss instead of in-batch negatives. And in the first stage, what you do is you only update your feature representation table per epoch. That means like you start by updating it, then you kind of compute fully softmax and like update your model parameters. But in the second stage, what they do is they do not touch the item feature table. It is frozen, and they only fine tune the model parameters. That means, yeah, like, I mean, there are no parameters in the item encode in feature table. It just get created with your RecFormer. But what they're saying is keeping that thing frozen is stable for the model to learn its best parameter setup, right? That's pretty much the paper. Actually, it's pretty good, and there are a bunch of experiments which I'm not going to go through it. And they also have like how they have pre-trained, how they have fine-tuned. So seems like fine-tuned data sets are quite small, that's why they can't use these in-batch negatives and all. Alright, this table actually shows all these ablation studies. I'm not going to go in details. You guys can always go through it if it is important. So I kind of always like to check ablation studies, especially from an industrial perspective. So yeah, like without 2-stage fine-tuning, what is the result? That means like you just, after the pre-training, you just use it. And this is like, if you don't use pre-training, what would be the result for different metrics? That means, I guess, you just use a long former and train with your own train with your own setup, then without item position embeddings and token type embeddings. So this means like, what if you just use the long former as is and execute this setup? Yeah, sometimes like when you closely check about it, like there's not much difference when it comes to some data sets like scientific, but instruments, yes. So they have some reasons for that, why why RecFormer performing really well for this data set especially. So yeah, just to like conclude, without 2-stage fine-tuning, we do not update item feature matrix I and only conduct fine-tuning based on I from pre-trained parameters. So that is the 2-stage thing. We find that compared to RecFormer, without 2-stage fine-tuning has similar results on scientific, but has a large margin on instrument, since pre-trained model has better pre-trained item representation on scientific compared to instruments. Yeah, like it makes sense. But I guess like maybe in instrument there are so many different items, and maybe their representations are very different from usual text. I don't know, you can check it. And our proposed 2-stage fine-tuning can be effectively improve the suboptimal item representation for pre-training. Then we investigate the effects of freezing trainable word embeddings and item embeddings. In our default settings, we freeze the item feature matrix I and train word embeddings of the RecFormer. That means now they have done mostly these ablation studies for the fine-tuning thing. So what they're saying is, okay, during the fine-tuning we freeze the item feature matrix and train word embeddings of the RecFormer. That means like thinking like it can improve the semantic features and all. Maybe the divergence can be eliminated by two-stage fine-tuning strategy. Without pre-training, fine-tunes RecFormer from scratch. We can see that RecFormer significantly outperform the variance of 5 in both datasets, because without pre-training, the item feature matrix I is not trained and cannot provide informative supervision during the fine-tuning, even if we update I by two-stage fine-tuning. Finally, we explore the effectiveness of our proposed model with structure, that is item, position, embeddings and token embeddings. Variant 6 removes 2 embeddings, and results show that model 6 causes performance decay on instrument dataset, which indicates one thing for me is I really want to like see how this one, like without position embeddings, without type embeddings, what if we train this on in-batch negatives like in the pre-training stage, and what might be the results. But I guess for that maybe you need a bigger data set, that's why they didn't do it. But that's pretty much it from me today, and this is like a nice paper. We had a quick read of it, so you can always go through this. Let me know if you have any questions, and please comment, like and subscribe. Thanks a lot. Bye bye.